It's hard to really get a sense of the CKY algorithm from staring at pseudocode, but I think if we work through an example, it'll actually seem pretty natural and straightforward. So let's do that. So starting off, here's the grammar that we're going to use. It's similar to the ones that I've shown before when we did the grammar transformations. It's a grammar with unaries, but with no empties in it. Okay, so there's only one conceptual leap that we have to make to get this to work, and that is, before I showed you parse triangles the natural way that makes sense, but it turns out that it's really hard to write text in diagonal diamonds, and so by and large what everyone has decided is that it's much easier to get human beings to tilt their necks 45 degrees to the right, and so they can see a parse triangle rather than to actually print things that way. So conceptually you should think about it just as we've had it before, that this is fish, people, fish, tanks. And so this is the first diagonal of the single words. This is the second diagonal of the pairs of words, the triples of words, and the four-word constituents. Okay, so what do we need to get going? We have our sentence to parse, fish, people, fish, tanks. The second thing that we need is the grammar. And so then once we've done that, we can start doing things. So in particular, what we're going to do is start filling in the lexical entries. So we start with the cell here, and we say, okay, the word fish, that can be a noun or a verb, and so we put in that we can make a noun from fish with probability 0.2, and we can make a verb from fish with probability 0.6. And then we keep on doing this for all the other cells along the diagonal. So people can be a noun with probability 0.5, and people can be a verb with probability 0.1. And we keep on going. And this is what we get. Okay, but now our grammar also has unaries that rewrite to categories. So we also then have to apply the unary rules. And so the way we'll do that is for each cell, we'll find unary rules that apply, and if they create a category that isn't there before, or one with higher probability than what was there before, then we'll put it into our chart. And in this case, the relevant unary rules here, we've got one other unary rule over here actually, are all creating different categories, so we'll be adding new things to the chart. So we'll say, look, we can also make a VP here which has probability 0.06. So there I'm taking the 0.1 and the 0.6 and multiplying it. We can make an NP where the probability of that is 0.7 times 0.2, 0.14. And in the first round through, that's all we'll do. But after we've been through all of the rules for non-terminals, we then say, well, we have added some new things, so added is true, and so we'll do this whole while loop once more. And we need to do that so we also discover that we can apply a second layer of unary rules and build an S over this span. So we'll also build an S, and the probability of that will be 0.1 times the probability of the VP, so that'll be 0.006. Okay, and so then we're going to apply the unary rules down the other cells of the lexicon. So at this point, we're ready to start doing the heart of the CKY algorithm, which is building constituents over bigger spans, first applying binary rules, and then we'll do the unaries again on top of them. Okay, so at this point, the cell that we next want to fill is this one. So this is the cell that's covering from words positions 0 to 2. So this version of the algorithm I've written using fence posts, even though the particular way I'm doing it, there aren't any empty elements. Okay, and so to build a binary constituent from out of this, the only way to do it is to build it something from 0 to 1 and something from 1 to 2. Well, the things from 0 to 1 are contained in this cell, and the things from 1 to 2 are contained in this cell. And so what we're going to do is consider ways of combining one of each of those to make some other constituent, which will be licensed providing there's a rule in the grammar over here of x goes to yz, where y is something here and z is something there. So what of that sort can we do? Well, there are no binary rules that have an n on the right hand side, only a unary rule, so we won't be able to do anything with the n. If we look at this v here, that could be made with that rule, so that's something that we can make. So look, we've got a VP goes to VNP, and so that means we can make a VP in this cell, and the probability of it will be 0.6 times 0.35 times the probability of this rule. And at this point you're starting to stretch my ability to do mental arithmetic, so that's 0.3 times 0.35. So that's 5 carry the 1, so 0.105. But then there are also other things that we can build with binary rules. So what other binary rules do we have? We've got a rule for S goes to NP-VP, and well, we can certainly apply that because we've got an NP here and a VP there, and so we can build an S over this span. And similarly for some other ones. So NP goes to NP-NP, or we've got an NP here and an NP there, so we can build an NP over this span. I won't try and work out all of the probabilities, but if we do that and apply them, we then end up with all of these probabilities here. Now it turns out that for each of the constituents that we built here in the binary phase, there's only one way of making them, so there wasn't any contention. But we'll be able to see contention at the next unary phase. And our rule for contention is always, if we discover multiple ways to make a category over a span, we keep the one of highest probability. And so the next phase here we now do is we do unaries for these cells down here. So again, we look for unary rules, and if they give a way of making something with higher probability, we put that into the chart, and then we say we've done some work, and having done some work will lead us to do the whole while loop again in case we're able to build up chains of unary rules. So in this particular case, there are no unary rules that have NP on the right-hand side, so we can't do anything there. But there is a unary rule that has VP on the right-hand side, and so we discover that there's another way that we can make an S, where we make an S goes to VP. And well, the probability of that is actually going to be 0.105 times 0.1, which is 0.0105, which is actually a lot more than the probability of this rule. So we're going to record a better way of making S in our back pointers, and we're going to record the probability of that new best way of making it. We always just keep what constituents we can make, the best probability way of making them, and if we're storing back pointers, the way that was the best way of making it. So if we go through all the cells and see if we can make them in better ways with unary rules, we find that that's possible in precisely two places. This one, and also over here, we find a better way of making an S. And so we update those two, and this is now the second row. Okay, so now we're going to go on to the third row where we're building 3-word constituents. So this is the fish people fish cell, and this is the people fish tank cell. So at this point, things get a little bit more interesting for building the binary constituents. So when we're going to build things in this cell, which are things from here to here, well, we're going to build binary constituents, but there are 2 ways that we can do it. We can either take something from here, from 0 to 2, and combine it with something from 2 to 3, or else we can take something from 0 to 1 and combine it with something from 1 to 3. And that's what we do in this part of the algorithm here. We choose a split point for dividing the constituent into 2. This is where we exploit it being only binary rules to get a cubic time algorithm. So we iterate across split points, which is another ON operation, and then we consider what rules that we can apply for each split point. And then that part is as we did it before. So first off, we're going to start with saying, okay, we're going to combine stuff from 0 to 2, that's this cell, with something from 2 to 3, that's this cell. And so then we'll see what we can build. And well, we have an NP and an NP, and so that will allow us to build a bigger NP according to that rule. And we have NP and a VP, so that allows us to build an S using this rule. And we have, well, it seems like we can't actually build a VP over that span doing things that way. Okay, let's then consider the other possibility where we do this and this. Well, this time we can build an NP by combining this NP and then looking for the other one, we're looking at this cell. So this time we're using these 2 cells. So we can use this NP and this NP, which will allow us to build an NP. We can use this verb and this NP, which will allow us to build a VP. And we can use this NP and this VP, which will allow us to build an S. And so we can build things with that span. And so then what we're going to want to do is say, okay, we can definitely build an NP over this span, but we want to find out which of these 2 is the highest probability way of making an NP and keep only that. And similarly, you're going to want to find out which of these 2 is the highest probability way of making an S and keep only that. Now actually, if you work through the math in this case, there's a little fine point for the NP case, because if you look at the NP case, for the purple one, it's 0.0049 times 0.14, and the probability of the NP rule is a constant 0.1. And if you go to the green one, it's 0.14 here, which is the same as there, and 0.0049, which is the same as there, reflecting the fact that both ways of doing it, you're using the word fish twice and the word people once. So actually both ways of making an NP have identical probability. So in practice, when you have ties like this, these parsers just choose one analysis, the first one they come across, but sort of you can just say they choose one analysis randomly. Okay, so that then fills in that cell and we get these numbers. And then at that point, we would again apply unary rules. So the only unary rule that's active at this level is this one, because the other 2 unary rules only work on N and V, and so aren't applicable in a cell like this in this little grammar. So we'd also find a new way of making an S that by making it from a VP, but its probability would be 0.1 times this number, so it would be 0.000147, which is less than the way we've already discovered of making an S, so we'll keep this as the highest probability analysis. Okay, so then we do this cell here, the 1 to 4 cell. And so again, there are two split points of ways of making it up. We can either make something from 1 to 2 and then 3 to 4, or else we can make something from 1 to 3 and then from 3 to 4. And so we explore all those ways of combining things and fill in this cell. Okay, now we're almost at the end. We just have to fill in the final cell of the chart. And it's the same thing, apart from now when we iterate across split points, there are 3 ways to do it. So you can make things to put in here either by taking things from 0 to 1 followed by 2 to 4, or you can have things that are from 0 to 2 plus things from 2 to 4. Or you can have things that are from 0 to 3 plus things from 3 to 4. And so we explore all the ways of combining things, and again choose the highest probability way of making each of a noun phrase, an S, and a VP, which are the 3 constituent types that we can build over that span. Now, by the time you've gone this far up, the math is much too difficult for me to do in real time in front of you, but I've worked it all out in advance, and if we fill it out, this is what we get. So what we get here is that we can just ask the question of what's the highest probability pars of this sentence, regardless of what category you choose for it. And the answer to that is parsing it as a sentence. But if you have a nominated start category like S, you can instead say, I just want to find an analysis as an S regardless, and then that will also return this analysis. Okay, I say we've finished, but actually, well, where is the parse tree? And so the answer to the parse tree is we can find it by now calling this build tree routine that traces backwards through the tree. And so we know that the first thing that we built at the top, just taking this starting point, is it's an S goes to NP VP. And at this point, I have to confess that I actually left a little bit out of what's written in the table just to keep things written larger. That rather than simply writing the rule that you used, you'll actually record which cells you built it from, so that these are actually constituents over spans. So this is actually a noun phrase that was built over 0 to 2, followed by a verb phrase that was built over 2 to 4. Okay, so that means we now look in the 0 to 2 cell to find the noun phrase. We look in the 2 to 4 cell to find the verb phrase. And at that point, we'll start to, so this is 0 to 4, 0 to 2, 2 to 4. And at this point we start to recurse downwards. So the highest probability way of building a noun phrase was using the noun phrase goes to noun phrase rule. And since that's a binary rule, we then necessarily know that it had to be 0, 1, and 1 to 2. And the highest way of making a verb phrase is using the verb noun phrase rule, where this goes from 2 to 3 and this goes from 3 to 4. Okay, so then that means we're building this noun phrase as a noun phrase in this cell, and we're building this noun phrase as a noun phrase in that cell, and then over here we're building the verb as a verb in this cell, and we're building the noun phrase as a noun phrase in this cell. So at that point we can then say, well, what's the highest way of building a noun phrase here? Oh, it's by making it as a noun from 0 to 1. Well, what's the highest way of making a noun over 0 to 1 from the same span, because that was a unary rule? Well, it was by realizing it as the word fish, which was a word in our sentence. And now similarly we do the same for the other cells. Okay, so from 1 to 2, the way of building a noun phrase with highest probability was building it from a noun as a unary rule, and the way of building a noun with highest probability was using the word people that's a terminal in the sentence. The highest probability way of building a verb from 2 to 3 is directly making it from the word fish, which is a terminal in our sentence, and then the highest probability way of making a noun phrase over 3 to 4 is from making it from a noun from 3 to 4 via unary rule, and the highest probability way of making a noun over 3 to 4 is making it using the word tanks, which is a terminal. So at this point we've been able to follow the back traces back out, and if can show you this is the highest probability pars for this sentence. Phew, that was a bit to get through for me as well as you, but I hope you can see it's actually fairly straightforward as an algorithm, and it's actually much easier for computers to do it than it is for human beings filling in squares of a rectangle.